Hello everyone, this is Mr. Kaviani, and by the end of this video, you should be able to interpret the meaning of the slope and y-intercept of a position versus time graph, and determine the speed of an object, the distances traveled, and the displacement of that object from a position versus time graph. Let's walk through an example of creating a position versus time graph, and this is the very same example we did together in class. Imagine that we have a constant velocity buggy car, and by that I mean it travels the same distance every second, and let's say that it has a speed of 20 centimeters every second. So you let it go, and at the beginning, it's there at the 0 centimeter mark. These are all going to be centimeters. And then after about 1 second, you see that it is now at the 20 centimeter mark, and you'll go ahead and mark that and say that was 1 second. After 2 seconds, the car is now at the 40 centimeter mark, and we'll go ahead and mark that on our timeline. After 3 seconds, the car is here at the 60 centimeter mark, and then after 4 seconds, the car is at the 80 centimeter mark at the 4-second timestamp. So what we've done is we've tracked the position of the car over time, and every second we've marked the position of the car on this number line. I've gone ahead and put this data from our experiment into a table on the left, and I'm going to graph it on the right, putting time on the x-axis and position on the y-axis. Pause the video and graph the data for yourself before continuing. Hopefully your graph looks something like mine on the right. Now again, your scale might be different and that's totally fine. But what we notice is we get a linear relationship, right? As the time increases, our position increases by the same amount for every segment of time. I'll show that with a line of best fit here. Now, it's important to know that when we look at a position versus time graph, the slope of this graph has a significant meaning, and we discussed this in our lab, right? The slope of this graph tells you how my position changes every second. So in a sense, the slope of this graph is my speed. So if I were to calculate the slope between any 2 points, I'll just go ahead and choose, let's see, these 2 points. This is 3, 60 and 4, 80. If I want to find the slope of this line, remember the slope is going to be our change in y over the change in x. That'll be my y2 minus y1 over x2 minus x1. I'll go ahead and call this x2 and y2, and this one x1 and y1. So my slope in this case would be 80 minus 60 divided by 4 minus 3, and that would give me 20 centimeters per second. Remember, it's the units of the y over the units of the x. And so again, I know that my slope is the speed of this car. We also know that the starting position is represented here by the y-intercept. And so in this case, I started my car at the 0 centimeter mark, and so at time t equals 0 seconds, I begin at the 0 centimeter mark. Let's take a look at another example. Now, let's say we took this same buggy car, but this time we release it from the 80 centimeter position, starting here, and then traveling to the left, so in the other direction. So at time t equals 0 seconds, the car will be at the 80 centimeter position mark. Then after 1 second, since the car is still traveling at a speed of 20 centimeters per second, after 1 second, I see that the car is here at the 60 centimeter mark. If I keep going, after 2 seconds, the car would be at the 40 centimeter mark. And let's say this time that the car hits a rock. So there's like a big rock in the road or something, and the car is stuck. So for 2 more seconds, the car is stuck. So the car is still here at 3 seconds, and then still here at 4 seconds, right? So time keeps going by, but the car's position is not changing. It's stuck in the road. And then right at the 4-second mark, you come in here and you take these rocks away, and the car begins to continue again in the path it was traveling in. And so then after 1 more second, the car is now at the 20 centimeter mark. And so that would be at the 5-second mark. The car is here at 20 centimeters. Now let's put this data into a table and then graph it. So I have our data from our second experiment in the table on the left. Let's go ahead and plot this data. So at 0 seconds, right, I am here at the 80 centimeter mark. So instead of starting down here, right, I'm actually starting here this time. At 0 seconds, the car started at the 80 centimeter position. That's where it was. And then after 1 second, the car was at the 60 centimeter mark. So I'll show that right here. After 2 seconds, the car was at the 40 centimeter mark. And then at 3 seconds, the car was still at the 40 centimeter mark. Remember, this is where the car got stuck behind the rock. And so the car was still stuck behind that rock, even at the 4-second mark. And so I'll show that right here. But then right at the 4-second mark, you took the rock away, and the car continued to travel in a constant speed of 20 meters per second backwards. And so at 5 seconds, the car ends up at the 20 centimeter mark. And I'll show that right here. So if I connect these dots then to sort of give you an idea about the general shape of the graph throughout this whole time, you see 3 distinct regions, right? We have, I'll call this region 1, region 2, and then region 3. And so what I can take a look at is the speed of the object during each of these 3 intervals of time, okay? So during the first interval, I know that my speed was still, it's the same car, it's still 20 centimeters per second, right? But in this case, the slope of this line, right, the slope here is negative. So if I were to do a quick calculation, right, I could take a look at this point, 2, 40, and this point right here, 0, 80. And if I were to calculate the slope using the same way, y2 minus y1 over x2 minus x1, I would get 80 minus 40 over 0 minus 2. That would give me a speed of negative 20 centimeters per second. So on this graph, this is actually my velocity, right? Because of the negative sign. The negative sign indicates the direction, right? That this car is moving backwards. And so before we had the car moving forwards, the line had a positive slope, but now because it's moving backwards, we have a negative slope. So a negative slope on this graph represents motion backwards. Now the slope is still the speed, so we haven't changed the actual steepness of the line, just the direction that it's heading in. Now for the second section, right here, the car is stopped, right? It's not moving. And so I could look at any 2 points on this line. We'll go ahead and use these 2 points. If I were to calculate the slope between these 2 points, right, that would be 40 minus 40 over 3 minus 2. That would be 0. So I can tell here that I have a speed of 0. And we just call that stopped, right? The car is not moving. So any flat region on this graph indicates that an object has stopped moving and is stationary. And then right here, again, during region 3, I see we have that constant speed of 20 centimeters per second. And if I were asked for the velocity, that would be negative 20 centimeters per second. Now, in this case, the speed is very similar to the velocity. It's just that speed is always positive because it's a scalar. And so if you're ever asked for the speed of an object, you'll drop the negative sign. But if you're asked for the velocity of that object, you would include the negative sign because that captures the fact that this car is moving backwards. Okay, so now you've seen a little bit more complex example of a position versus time graph that doesn't start at 0, right? So now my starting position here was 80 centimeters. It has sort of a negative velocity, means it's moving backwards. It stops and then continues to move backwards at that same speed. Now, if I asked you, what was the car's distance traveled in this case? Well, I can think about where the car started, right here at 80. I'll circle this. And then the car went all the way to 20. And so that I know the car traveled a distance, I'll write that up here, a distance of 60 centimeters. And in this case, what was the car's displacement? Well, the displacement I could say is negative 60 centimeters. Again, the negative sign indicates that the car is to the left or ends up sort of in the backwards direction from where it started. So that's another way that you can also use this graph to find out the distance and displacement of an object. Go ahead and watch the next video on Canvas for a more complex example where we'll go through each of these steps in depth.